So we've looked at integrating a whole lot of different quotients. We had ones where we could divide ourselves just by cancelling out as we go. We had ones where we had to do that long division so that we got something that was just over an x. And the third type is this particular type where the numerator is actually the derivative of the denominator. Now, it doesn't have to be the exact derivative. It could be a multiplier of the derivative. So instead of being x plus 3, it could be 2x plus 6. That would still have to be recognised. So to use this particular one, you actually have to look for it first. All right? So the idea is that this one will come bouncing out at you because you'll see that that's... The other thing that's probably quite true in this particular case is the denominator is a higher powered polynomial than the numerator. In other words, it may have an x squared where the numerator will have an x. If it's an x cubed, you would expect the numerator to have an x squared because that's the derivative of x cubed. All right? And if that is the case, then the integral of this is equal to absolute values. This. Now, we've had a little rule up till now that we can only do this if we have an x only on the bottom. But this is an exception to that rule in that this is a technique. All right, so let's have a look at an example.
Right, is supposed to be a dx?
Yes, it'd be a dx here. Would be correct. Pierce will know that because it's missed out in his assignment. And they made a note of it. Okay, so we've got if we were looking at the other ones, right, this is not going to divide very nicely into this, okay? Because there are two terms on the bottom and only one term on the top, we're not going to split it up. If it was upside down, it would be fine. We'd split it into the two terms, simplifying as we go. So it kind of gives you the idea that perhaps this is where we were going anyway. So what we've got here is that this part, f of x, is equal to 3x squared plus 5. And when we differentiate that, we get 6x, which in this case happens to be a perfect match. All right, so because it's a perfect match, when we actually end up, that's not correct. Don't write that one. And that's quite important. And when we actually integrate this, I mean, we would end up with that. So this will equal ln of 3x squared plus 5 plus 6. All right. So if we were going to differentiate this, just to check it, so if we were differentiating ln of 3x squared plus 5, we would, plus c, obviously the c is going to go away. This would become 1 over 3x squared plus 5 times by the differential of what's in the brackets, 6x. Yes, okay, that's absolutely perfect. We're good to go. Can you see how that works? Yes. Okay, let's have a look at another one. All right, so we've got our derivative. Our f of x, we're saying, is the denominator, 5x squared minus 1. F dashed of x, take the power, multiply by, decrease the power by 1, and we'll get rid of the minus 1. So we've got 10x. So this time we don't have the whole amount of it. So therefore we have to do that compensating thing. So what we're actually saying is we've got a fifth of it. Right? 2x, 10x, we've got a fifth of it. So we'll have a fifth of the answer. All right, so we're going to end up with correct, thank you, plus C. All right, so we've located that that is a derivative of this, but it's not exact. We've only got a part of that derivative. It's the top. So if we had a fifth of this, if we differentiate this, this would turn into 1 over 5x squared minus 1. It would differentiate to 10x, and then we'd take a fifth of that 10x is 2x. So you can always check you're right by differentiating it backwards again. Okay. Okay, yeah, that's it. Good. We don't need a reminder.